Good morning. My presentation title is Toward Geometric Interpretation of Generalized Frequency. And the purpose of this presentation is to introduce the vector bundle framework of extended frequencies, which is geometric algebra valued vector fields on surfaces. And the aim of this research is to give a geometrical interpretation of the generalized frequency by Federico Milano in the framework. And its main theorem, I will explain about this and with an example. And let me share the outline of this presentation. First, let me review the geometric algebra, and second, a generalized frequency will be introduced and an example will be given. And third, extended frequency will be introduced and an example will be given. And fourth, the characterization theorem will be introduced. And finally, I will give a geometric interpretation of generalized frequencies. So let me explain about geometric algebra. Let Rn plus 1 has an orthogonal basis E1, E2, n plus 1, and geometric algebra Krn plus 1 and O dot is a unitary associative algebra with O dot and its product called geometric product, and it satisfies these properties. So Krn plus 1 spanned by these bases, real number 1, E1, EI1 O dot, O dot EIP, and P runs from 1 to n plus 1, and E1 EIP runs from 1 to n plus 1. And the second, EI O dot EJ is equal to 1 if I go j, and otherwise it is equal to minus EJ O dot EI. And third, X O dot Y plus Y O dot X is equal to 2 times X dot Y, and X dot Y is a canonical inner product in Rn plus 1. And especially, square of X is equal to square of magnitude of X and its real number. And let me introduce the extended inner product burette and extended outer product wedge here in this way. So this geometric product or AO dot B is equal to the sum of A burette B plus A wedge B. So let me introduce the generalized frequency of Milano. So let V be the curve in Rn plus 1 and its infinite function. So generalized frequency is the function from C infinite I Rn plus 1 to C infinite I J Rn plus 1. It's geometric algebra, and it's the function defined by this right-hand side, and which V square of V is the magnitude of V. And this term, described by small rho V, is called radial frequency, and this term, described by large omega V, is set V frequency. So thus, generalized frequency defined by Milano, its Fv, is described by rho V plus large omega V. And when P equals V0, Fp is calculated like this right-hand side. So let me show the example of generalized frequency. So V is the voltage curve in R3 and defined by this. So it's the circle in R3, and its radius is square root of 3 over 2, 2 over 3, and omega 0 is the positive constant, and alpha is equal to 2 over 3 times pi. And then we calculate the generalized frequency. Fvt is as this, and its magnitude of generalized frequency is equal to omega 0. So generalized frequency is the extended concept of frequency. And let me introduce the extended frequency. So D is the open subset in Rn plus 1, and F is the infinite function from D to R. And X is the vector field on D and its infinite vector field. And S tilde is the n surface defined by F. and I is the identity map on S. So the pair SFX is extended frequency associated with X if and only if Fx is the function from S to Grn plus 1, and the symmetry function is defined by this right-hand side, and the extended frequency at the P in S is calculated as below. And let me introduce the tangential condition. So extended frequency SFX is tangential at the P in S if and only if xp dot gradient of P is 0, and it's canonical in the product. And extended frequency SFX is tangential on S if and only if for every P in S, xp dot gradient of P equals 0. And let me show an example of tangential extended frequency. So let S is the sphere in R3, and radius is square root of 3 over 2, and the center is the origin, and X is the vector field on S, defined by this. And H denote the set of all points in R3 satisfying X plus Y plus Z equals 0, and SH is defined by intersection of S and H. So for P in SH, the extended frequency calculated at right-hand side, and then the extended frequency is tangential, and magnitude of fxp is equal to omega 0. So let me use the graphic to explain the tangential extended frequency. So S is the sphere in R3, and H is this red plane, and SH is the intersection S and H, so its green circle is SH. And we calculate fxp on SH. So SH, extended frequency, SHFX is tangential only on this SH. And magnitude of fxp is equal to omega 0. So it's extended concept of general frequencies too. And its example suggests this theorem. So a generalized frequency of Milano associated with each voltage curve coincide with the tangential extended frequency. So the tangential condition plays an essential role in the above theorem. And next, let me introduce the geometric algebra valued bundle. So a pair GSG Rn plus 1 and pi is the geometric algebra valued bundle if and only if S is the n surface in U and U is the open domain in Rn plus 1. And for any P in S except 0, GPS is defined by injective limit C infinite U G Rn plus 1 and P in U. And GS G Rn plus 1 is defined by disjoint union GPS G Rn plus 1, and P runs over S except 0. And pi is the canonical projection from GS G Rn plus 1 to S. And then we obtain the proposition. First, GPS is a geometric algebra, and the second, GS G Rn plus 1 has a topology induced from the surface S where the projection pi being continuous. And let ES is the set of all fx, extended frequency fx, and x is the infinite function, vector field on S. And by a geometric interpretation of generalized frequency, we mean characterization of ES in the framework of geometric algebra bundle GSK Rn plus 1. And let TPS the set of all fxp in G Rn plus 1. A pair TS pi is tangential vector bundle of the generalized frequencies of S if and only if TS is defined by disjoint union TPS and P runs over S except 0, and pi is the canonical projection TS to S. And we reconsider about the characterization theorem in this framework. So its characterization theorem, generalized frequency coincide with the tangential extended frequency. So it rewrite in this framework. So its all generalized frequencies on S and its tangential vector bundle, and it's equal. And especially for any p in S except 0, there exists the surface in SP such that MPS is equal to TPSP. And we obtain the corollary. Let HPS its tangent hyperplane of S at P. For any P in S except 0, MPSP is linearly isomorphic to HPS. And by using this corollary, we obtain the main theorem. So the generalized frequency, all generalized frequency over S is linearly isomorphic to tangent hyperplane over S. So let me show the example of main theorem. So S is the set of all x satisfying square magnitude of x is equal to square root 3 over 2 and x plus y plus z equals 0. And MS is the all generalized frequencies on S, and HS is the all tangential hyperplane over S. So then HS is described by this right-hand side, and it's linearly isomorphic to MS. So let me use the graphics of main theorem to explain main theorem. So S is this green circle, and this plane is tangent hyperplane at P in S, and its hyperplane at Q in S. So this is S, surface S, and each point had the hyperplane as this, and its all hyperplanes is HS and is linearly isomorphic to MS. So the main theorem, the class of the generalized frequencies is linearly isomorphic to the vector bundle consisting of all the tangent hyperplanes at any point of the surface S. And we propose the structure of the geometric algebra valued vector bundles, and we address a geometric interpretation problem of generalized frequencies of Milano, and we obtain the interpretation of the above main theorem. So that's all. Thank you for your attention.